Somewhere out there, in the quiet dark between the stars, something extraordinary is spinning. It is smaller than a city, yet it outweighs the sun. It is so dense that a single teaspoon of its material would tip the scales at roughly 1 trillion kilograms, more than the combined mass of every human being who has ever lived, compressed into a space no larger than a sugar cube. It is, by almost any measure, one of the most extreme objects the universe has ever produced. It is a neutron star. Tonight we are going to spend some time with these remarkable objects. We will move slowly, and there is no hurry. The universe has been making neutron stars for billions of years, and it is in no rush, neither are we. So let your breathing slow, let the weight of the day begin to lift. Let the noise of whatever filled your hours gradually become quieter, and allow yourself to simply drift through the science. Because the story of neutron stars is, in its own strange way, one of the most peaceful stories in all of astronomy. It is a story about what remains when everything else falls away, about the quiet persistence of collapsed things, about objects that were forged in some of the most violent events the cosmos can produce, and that have spent billions of years since then simply cooling, slowly, patiently, without urgency, in the vast and gentle dark between the stars. We have 101 facts to share with you tonight. Some of them will be numbers so extreme they may feel more like poetry than physics. Some of them will be concepts, ideas about the nature of matter and gravity and time that physicists have spent decades working out, and that neutron stars have spent billions of years quietly embodying. And some of them will simply be images, pictures you can hold gently in your mind before you let them go and drift a little further towards sleep. There is no test at the end. There is nowhere you need to be. The neutron stars will still be out there when morning comes, spinning and cooling and carrying their extraordinary secrets through the dark. And so, without further waiting, let us begin. A neutron star is the collapsed core of a massive star. What is left behind after that star lived its long and brilliant life and died in a tremendous explosion called a supernova. When the outer layers of the star are blasted outward into space, the inner core, suddenly stripped of all its support, falls inward under the crushing weight of its own gravity. The collapse takes less than a second. In that fraction of a second, something extraordinary is created. What remains is an object of almost impossible density. The atoms that once made up the core are compressed so tightly that they no longer exist as atoms in any conventional sense. The electrons are forced into the protons. The protons become neutrons. The space between the particles, which, in ordinary matter, is vast compared to the particles themselves, is essentially eliminated. What is left is a sphere of neutrons, packed together as tightly as physics allows, held together not by the strong nuclear force that binds an atomic nucleus, but by the crushing weight of gravity itself. For a neutron star to form, the leftover core needs to contain roughly 1 to 3 times the mass of our own Sun. This is a precise and somewhat delicate balance. Too little mass, and the collapse produces a white dwarf, a dense but comparatively gentle stellar remnant, the fading ember of a smaller star. Too much, and the collapse does not stop at a neutron star at all. It keeps going, past every known threshold, compressing the matter past the point where even neutron pressure can resist, and a black hole is born. Neutron stars exist in that narrow, extraordinary window between the two extremes, too dense to be anything ordinary, not dense enough to disappear entirely. They are, by current understanding, the second densest known stellar objects in the universe, surpassed only by black holes themselves, which are in a category so extreme they can no longer be said to have a surface at all. A neutron star, by contrast, does have a surface. You could, in principle, point to it on a diagram and say, there. That is where the star ends and space begins. It is just that nothing you could ever build would survive anywhere near it, and nothing you could ever throw at it would reach the surface intact. Let us take a moment to appreciate what the numbers actually mean, because they are the kind of figures that, if you let them settle in your mind rather than skimming past them, are genuinely astonishing. Numbers so extreme that they stop feeling like numbers and start feeling like something else. some kind of surreal poetry written by physics for its own private amusement. A typical neutron star has a radius of about 10 to 12 kilometers. That is roughly the size of a large city. If you placed a neutron star in the center of a metropolitan area, it would extend almost to the edges of the suburbs, still entirely within the city limits. You could drive across one in about 15 minutes at highway speeds. If there were roads, if you were not immediately vaporized by the radiation and gravity and the general hostility of the environment. Within that city-sized sphere sits more mass than the entire Sun. Our Sun, which is so large that more than 1 million Earths could fit inside it. Our Sun, which accounts for over 99% of all the mass in the solar system. All of that mass compressed into something you could walk across in a quarter of an hour if you could walk. That is a neutron star. The density that results from this compression is almost impossible to convey with ordinary analogies, but we can try. Their average density is roughly that of an atomic nucleus, the tiny, incomprehensibly small core at the heart of every atom in the physical world around you. Every atom in your body, in the air you are breathing, in the room you are in, has a nucleus at its center smaller than 1/1,000,000th of a centimeter across. That nucleus is dense. A neutron star is that dense, sustained not across the width of a single atom, but across the width of a city. Every cubic meter of neutron star material contains the equivalent of about 100 million metric tons. That teaspoon of neutron star material, the one that weighs around 1,000,000,000,000 kilograms, is not a poetic exaggeration or a rough estimate rounded for effect. It is a straightforward consequence of the density involved. Pick up any teaspoon, fill it with neutron star material. It would contain more mass than all the water in all the oceans of Earth combined. That is what gravity, pushed past the point of ordinary endurance, is capable of doing to matter. The name gives it away mostly. Neutron stars are composed primarily of neutrons, the electrically neutral particles that, in ordinary atoms, live packed inside the nucleus alongside protons. The proton is the positively charged particle. The neutron is its neutral companion, and together they form the atomic nucleus that sits at the heart of every element in the periodic table. In a neutron star, the conditions are so extreme that the distinction between proton and electron and neutron begins to collapse. The enormous pressure forces electrons into protons in a process called inverse beta decay, producing neutrons and releasing a flood of neutrinos. What remains is an object made almost entirely of the densest, most tightly packed neutrons physics permits, hence the name. A small fraction of protons and electrons persist alongside the neutrons, scattered through the interior in proportions that vary with depth. They are the minority, passengers rather than rulers in this extreme environment. And crucially, many of the neutrons inside a neutron star are what physicists call free neutrons. Neutrons that are not bound inside any atomic nucleus, not sitting in a tidy crystalline lattice, but existing as a kind of dense quantum fluid, governed by rules quite unlike anything we encounter in the everyday world of solid objects and familiar chemistry. The interior of a neutron star is, in a very real sense, one of the last great unknowns in fundamental physics. We can observe its surface with X-ray telescopes. We can measure its spin period with radio dishes, its mass through orbital dynamics, its magnetic field through its radio emissions. But what happens in the deepest layers, in the innermost core where the pressure exceeds anything we can reproduce in any laboratory, we are still working out. The answer may involve forms of matter that do not exist anywhere else in the known universe: hyperons, quark, gluon plasma, strange matter. The neutron star keeps its deepest secrets well. When a neutron star is born, in the extraordinary violence of a supernova explosion, it arrives into existence at a temperature of around 10 billion Kelvin. Pause on that for a moment. 10 billion Kelvin. For context, the surface of our Sun is about 6,000 Kelvin. The core of the Sun, where nuclear fusion is actively occurring, reaches about 15 million Kelvin at its hottest. A newborn neutron star is roughly 600 times hotter than the Sun's core. In those first moments after formation, it is one of the hottest objects in the observable universe. And yet it cools with remarkable speed. The mechanism behind this cooling is not ordinary heat radiation. Neutron stars are not simply glowing objects slowly losing warmth to their surroundings the way a hot coal cools in open air. The cooling is driven primarily by something far more exotic, an intense, almost unimaginable flood of neutrinos pouring out of the star in every direction. Neutrinos are ghostly particles, nearly massless, carrying no electric charge, and interacting with ordinary matter so weakly that they can pass through light years of solid lead without being stopped. Normally, this makes them nearly undetectable. But in the extreme density of a newborn neutron star, even neutrinos cannot escape freely at first. They scatter and interact, gradually diffusing outward over the first few tens of seconds after formation. As they escape, they carry energy with them, enormous, staggering quantities of energy. During those first seconds of a neutron star's life, the neutrino emission can carry away energy comparable to all the light produced by all the stars in the observable universe over several seconds. All of it, channeled through an object the size of a city, pouring out in the form of particles that barely interact with anything at all. It is one of the most extreme energy release events in all of physics, and it is entirely invisible to ordinary light-based telescopes. Within just a few years, the temperature plunges from 10 billion down to around 10 million Kelvin, a drop of a factor of 1,000 in what is, cosmically speaking, the blink of an eye. And at 10 million Kelvin, the neutron star settles into a different mode of cooling, slower now, driven by ordinary thermal radiation. At this temperature, the peak of its emission falls in the X-ray band rather than visible light. This is why we need space-based X-ray telescopes to study neutron stars. They glow steadily and beautifully, but not in any wavelength our eyes could detect. Here is something worth pausing on, because it changes how you picture these objects. A neutron star is not burning. There is no nuclear fire at its centre, no fusion reaction converting lighter elements into heavier ones and releasing energy in the process. The great engine that powered its parent star for millions of years, that long, sustained cascade of nuclear reactions working its way up the periodic table from hydrogen to helium to carbon to oxygen and eventually to iron, that engine has stopped. The neutron star is not powered by nuclear fusion. It never will be again. Instead, it shines from two sources. The first is residual heat, the slow, steady release of thermal energy accumulated during its formation and compressed into its dense interior. Like a brick pulled from a furnace and left to cool on a table, a neutron star simply radiates the heat it already contains. In ordinary objects, this process happens quickly. In neutron stars, the density and composition of the interior slow the cooling dramatically, allowing them to remain detectable X-ray sources for tens of thousands of years or more. The second source, in some cases, is accretion, the process of drawing in material from a nearby companion star. When a neutron star has a binary companion, it can gravitationally strip gas from the companion's outer layers. That gas spirals inward, forming a disk, heating to extreme temperatures as it falls, and releasing energy as X-rays. Accreting neutron stars can be extraordinarily bright, among the most luminous X-ray sources in the sky, but the great engine of fusion that once made its parent star shine across millions of light years, that is gone. The neutron star is, in the most literal sense, the cooling ember of what was once a fire. There is something quietly moving about that image. If you let it sit, the fire has gone out, and what remains is something denser and stranger and, in its own way, more permanent than the fire ever was. The surface gravity of a neutron star is hundreds of billions of times stronger than Earth's gravity. Earth's gravity is what keeps you in your chair, what makes rivers flow downhill, what holds the atmosphere in place. It is the gravity that gives weight to everything you have ever picked up or set down. A neutron star's gravity makes Earth's gravity seem like a gentle suggestion. If you could somehow stand on the surface of a neutron star, which is not physically possible for any collection of atoms arranged in any configuration we know of, you would weigh approximately 10 billion times what you weigh on Earth. If you dropped a marshmallow from 1 meter above the surface, it would strike the surface with roughly the kinetic energy of an atomic bomb. It would not land gently. Nothing lands gently on a neutron star. This gravity does something remarkable to light itself. We are used to thinking of light as something that travels in straight lines, and in ordinary flat space it does. But gravity curves space, and in the vicinity of a neutron star, that curvature is extreme enough to visibly bend the paths of photons. Light curves around the star. The consequence of this is almost poetic. Because light bends around the surface, an observer looking at a neutron star from a distance can actually see parts of the far side, regions that, on an ordinary solid sphere, would be geometrically hidden from view. The star's own gravity acts like a lens, folding portions of its far surface into visibility. You see more than you should be able to see. The star reveals itself from behind itself. General relativity makes the universe slightly more generous with information than classical geometry would suggest. The escape velocity from the surface of a neutron star is a significant fraction of the speed of light, meaning that even light climbing out of that gravitational well loses energy in the process. It shifts toward the red end of the spectrum in what is called gravitational redshift. This shift is not just a theoretical prediction of general relativity, but a measurable quantity that tells us something specific and real about the depth of the gravity involved. Astronomers can, in principle, use this redshift to constrain the mass and radius of a neutron star, to weigh and measure an object 1,000 light-years away. Not just any star can become a neutron star. The process requires a specific kind of progenitor, a massive star, one that started its life with at least 8 times the mass of our own Sun, and that spent millions of years burning through its nuclear fuel at a furious rate before finally running out and collapsing. The upper limit is a bit blurrier, but stars in roughly the 8 to 25 solar mass range are the most common candidates to leave a neutron star remnant. At the upper end of that range, and beyond, the collapse is likely to carry past the neutron star stage entirely and produce a black hole. The precise boundary depends on the composition of the star, its rotation, and details of how the supernova explosion unfolds, details that astronomers and computational physicists are still working to understand. When such a star finally exhausts its nuclear fuel, after millions of years of fusion that worked its way progressively up the periodic table, from hydrogen to helium to carbon and oxygen and silicon, and finally to iron, which cannot release energy by fusing further, the core collapses in a fraction of a second. The collapse is essentially instantaneous by human standards. The core, which may have contained more than a solar mass of material spread over roughly the size of Earth, collapses to a sphere 12 kilometers across in about 1/10 of a second. The outer layers, suddenly unsupported by the pressure that was holding them up, fall inward and crash into the stiffened neutron core, rebounding outward in a shock wave that tears the star apart. The outer layers are blasted into space as a supernova. For a few days or weeks, the exploding star shines as brightly as an entire galaxy of hundreds of billions of stars. And at the center of all that light and violence, a neutron star is born, already cooling, already spinning, already carrying the information that will eventually allow us to probe the physics of matter at its most extreme. The Crab Nebula, visible in the constellation Taurus as a beautiful tangled cloud of glowing gas, is one of the most famous examples of this process in our own galaxy. The supernova that created it was observed by astronomers in China, Japan, and the Arab world in the year 1054. It was so bright that it was visible in daylight for weeks and could be seen with the naked eye for nearly 2 years. Nearly 1,000 years later, we can still see the expanding shell of gas, still glowing from the energy injected by the explosion. And at the heart of it, the neutron star, still there, still spinning 30 times per second, still cooling. When a massive star collapses, it spins up dramatically. This is the same physical principle that makes a figure skater pull in their arms and spin faster, conservation of angular momentum. The total angular momentum of a system, in the absence of external torques, remains constant. If the radius decreases, the rotation rate must increase to compensate. The parent star may have been rotating slowly by the time it collapses, perhaps once every few days or once every few weeks. but as its core collapses from something roughly the size of Earth down to a sphere 12 kilometers across, a reduction in radius by a factor of hundreds, the rotation rate accelerates by the square of that ratio. Something that was spinning once per month can become something spinning dozens or hundreds of times per second. Newly formed neutron stars can spin anywhere from a few times per second to many hundreds of times per second, depending on how much angular momentum their parent core had and how the collapse unfolded. The fastest known neutron stars push this to extraordinary extremes. The current record holder rotates at approximately 706 times per second, more than 700 complete rotations every single second. At its equator, the surface of that neutron star is moving at roughly 24% of the speed of light. In absolute terms, that is about 72,000 kilometers per second, fast enough to circle the entire Earth nearly twice in 1 second. Neutron stars can also receive what astronomers call a kick during the supernova explosion. The explosion that creates a neutron star is rarely perfectly spherical. There are asymmetries in the way the shockwave propagates, in the way neutrinos escape, in the way the infalling material flows. These asymmetries can result in a net thrust in some direction, like an uneven rocket firing, that pushes the newborn neutron star in one direction at high velocity. Some neutron stars have been measured moving through the Milky Way at hundreds of kilometers per second, flying away from their birthplace, gradually leaving behind the region of space where they were born. Over millions of years, they drift far from their parent stellar neighborhood. Some may eventually be ejected from the galaxy entirely, drifting off into intergalactic space, carrying their extraordinary density and their spinning magnetic fields out into the void between the galaxies. Many neutron stars emit powerful beams of electromagnetic radiation from regions near their magnetic poles. The exact mechanism is complex and still an active area of research, but the result is a focused beam, or sometimes two beams, one from each magnetic pole, that sweeps through space as the neutron star rotates. If Earth happens to lie in the path of one of these beams, we detect a brief, sharp pulse of radiation with each rotation of the star. We call these objects pulsars. The word pulsar comes from pulsating radio source, reflecting how they were first detected, as repeating pulses of radio emission arriving at Earth with extraordinary regularity, regular enough in fact, that the first discovery caused some genuine uncertainty about what was producing the signal. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, then a graduate student, and her supervisor Anthony Hewish at the Mullard Radio Astronomy Observatory in Cambridge. The signal was so precise and so regular that, for a brief period, it was actually designated LGM1 for Little Green Men, because no known natural process seemed capable of producing such clock-like periodicity. The Little Green Men turned out to be a spinning neutron star with a beam sweeping past Earth every 3 seconds, which is, in its way, considerably more interesting. Pulsars emit across the electromagnetic spectrum. Radio is the most commonly detected band, but pulsars have been observed in optical light, X-rays and gamma rays as well. Not every pulsar emits in every band. The mix depends on the age of the pulsar, the strength of its magnetic field, and the geometry of the emission region. The Crab pulsar, the young neutron star at the center of the Crab Nebula, is one of the few pulsars detected in essentially every band from radio to very high-energy gamma rays. The regularity of pulsar timing is one of the most remarkable properties these objects possess. The best millisecond pulsars, which we will discuss shortly, keep time with a precision that rivals, or in some cases exceeds, atomic clocks. This extraordinary precision makes them extraordinarily valuable instruments for a wide range of experiments in fundamental physics and astronomy, allowing measurements that would be impossible by any other means. Among the population of known pulsars, there is a special and fascinating class, millisecond pulsars, which spin with periods of just a few thousandths of a second, rotating hundreds of times every second, far faster than any newly born neutron star. They are not young, violently spinning objects fresh from a supernova. In many cases they are quite old, billions of years old, remnants of stars that died long before our solar system formed. So how did they get spinning so fast? The answer lies in binary evolution. When a neutron star exists in a binary system with a companion star, a star still living its normal stellar life alongside the neutron star, it can, under the right conditions, gravitationally strip gas from the companion's outer layers. This mass transfer begins slowly and then, depending on the system, can accelerate dramatically. The gas that falls toward the neutron star does not fall straight in. It carries angular momentum, so it spirals inward, forming a flattened disk, an accretion disk, that orbits the neutron star before gradually descending toward the surface. As material from the accretion disk reaches the neutron star's surface, it delivers angular momentum along with mass, like a hand spinning a top. Given millions of years and enough accreted material, this process can spin a neutron star up from a slow, aging pulsar, spinning perhaps once per second, to a millisecond pulsar, spinning hundreds of times per second. The old neutron star is essentially given a new lease on rotational life by its companion. Astronomers sometimes call this recycling, and the resulting millisecond pulsars recycled pulsars. During the recycling process, the system is also an intense X-ray source. As gas falls from the companion and spirals down through the accretion disk, it is heated to tens of millions of Kelvin and radiates brilliantly in X-rays. These accreting neutron star systems are among the brightest X-ray sources in the sky, visible across large fractions of the galaxy, and they have been the subject of intensive study for decades as laboratories for extreme accretion physics. If neutron stars were merely very dense and very rapidly spinning, they would already be among the most extreme objects the universe produces. But they also possess something else: magnetic fields of almost unimaginable intensity, fields that make the strongest magnetic fields producible in any laboratory on Earth seem negligible by comparison. A typical pulsar has a magnetic field roughly 1 trillion times stronger than Earth's magnetic field. Earth's field is strong enough to align compass needles, to deflect charged particles from the solar wind, to protect our atmosphere from erosion. It is a real and important field. A pulsar's field would render that comparison meaningless. It is strong enough to fundamentally alter the structure of atoms themselves, distorting the electron clouds of atoms into shapes quite unlike the familiar spherical orbitals described in chemistry textbooks, forcing them into elongated, cylindrical geometries aligned with the field direction. The energy stored in such a magnetic field is itself enormous. As the neutron star spins, its rotating magnetic field is constantly losing energy, radiating electromagnetic waves, accelerating charged particles, driving the pulsar beam that sweeps through space. This is how pulsars slow down over time. They are converting their rotational kinetic energy through the agency of the magnetic field into radiation and particle winds that flow outward into the surrounding space. But even typical pulsar magnetic fields are not the most extreme case in the neutron star population. That distinction belongs to magnetars, a special class of neutron star with magnetic fields up to 1,000 times stronger than normal pulsars. Magnetar fields can reach 10 to the 14 or 10 to the 15 Gauss. These values are so far beyond ordinary experience that they require a brief pause. The strongest magnetic field ever produced in a laboratory, using enormous, carefully engineered magnets drawing enormous amounts of power, reaches about 45 Tesla. A magnetar's field is roughly 1 billion times stronger than that. In these objects, the magnetic field is not merely a feature. It is the defining fact of the object's existence, shaping its structure, driving its activity, and eventually cracking its surface like an eggshell. A magnetar is a neutron star in which the magnetic field has become so overwhelming that it dominates almost every aspect of the object's behavior. This is not a small difference from an ordinary pulsar. It represents a genuinely different mode of existence, as different from a typical pulsar as a hurricane is from a gentle breeze. Where an ordinary pulsar slows down, primarily because it is radiating electromagnetic energy into space, losing rotational energy at a rate determined by the strength of its field and the rate of radiation. A magnetar's slowdown is driven largely by the field itself, which exerts powerful internal and external torques and continuously converts rotational energy into heat and radiation and magnetic stress on the crust. Magnetars are prone to outbursts, sudden, violent releases of enormous amounts of X-ray and gamma-ray energy. These bursts occur when the intense magnetic field builds up stresses in the solid outer crust of the neutron star. Think of it as magnetically induced tectonic activity until the crust fractures. Imagine the crust of the star, made of the densest and hardest material in the universe, cracking under magnetic pressure so extreme that even neutron star crust cannot withstand it. The energy released in these fractures, these starquakes, emerges as intense bursts of X-rays and gamma rays, sometimes detectable by satellites in Earth orbit from tens of thousands of light years away. The largest of these events are called giant flares. In December of 2004, a magnetar in our galaxy called SGR 1806-20 released one of the most energetic events ever observed in the Milky Way. The burst was so intense that, from 50,000 light-years away, it measurably disturbed Earth's ionosphere, the upper layer of our atmosphere, for several minutes, causing disruptions in low-frequency radio reception. A flash of magnetic radiation from a neutron star on the far side of the galaxy, powerful enough to leave a fingerprint on Earth's atmospheric chemistry. The universe, on occasion, is impressively violent even at enormous distances. Some magnetars show repeated bursting behavior with a characteristic period of a few seconds, placing them in a category called soft gamma repeaters, objects that periodically remind us they are there with high-energy flares that carry more energy than the Sun emits in thousands of years. Despite being only about 12 kilometers from surface to center, a neutron star is a surprisingly layered and complex object. Each layer represents a distinct physical regime, a different kind of matter under a different set of conditions, governed by different physics. Moving inward through a neutron star is, in a sense, moving through a tour of extreme states of matter. At the very top is a thin atmosphere, only a few centimeters deep. It is composed of light elements, hydrogen, helium, perhaps carbon, and it glows in X-rays, producing the thermal emission that space-based telescopes detect. This atmosphere is simultaneously the thinnest part of the neutron star and the part most directly accessible to observation. Beneath the atmosphere is the outer crust, a solid layer of atomic nuclei arranged in a crystalline lattice surrounded by a sea of degenerate electrons. The nuclei here are not the familiar nuclei of everyday chemistry. They are extremely neutron-rich, stuffed with far more neutrons than any stable nucleus in ordinary matter. They are held in their lattice positions by the electromagnetic forces between them and the electron sea, while the enormous pressure from above provides the overall structure. This outer crust is solid, in much the way ordinary solid materials are solid, though the nuclei and electrons it contains are nothing like those in ordinary solids. As you descend deeper, the pressure rises, and the nuclei become progressively more neutron-rich until you reach what is called the neutron drip point, a boundary below which the nuclei can no longer hold any additional neutrons and free neutrons begin to leak out into the surrounding space. Below this point is the inner crust, a mixture of neutron-rich nuclei embedded in a sea of free neutrons, a phase of matter that simply does not exist anywhere else. Deeper still, the nuclei dissolve entirely, and you enter a region of uniform nuclear matter, a dense fluid of neutrons with a small admixture of protons and electrons, potentially exhibiting the exotic quantum properties of superfluidity and superconductivity. And at the very center, in the innermost core, the density exceeds even this, and current physics becomes uncertain. There may be hyperons, heavier, strange, quark-containing cousins of the neutron. There may be quark matter, in which the quarks that ordinarily make up protons and neutrons are no longer confined inside individual particles, but flow freely as a new phase of matter. There may be a condensate of pions or kaons. We genuinely do not know, and this uncertainty is not a failure of physics, but an honest admission that we are at the edge of what our theories confidently describe. One of the most intriguing windows into the inaccessible interior of a neutron star is a phenomenon called a glitch. Occasionally, without warning and without any obvious external trigger, a pulsar will suddenly and very slightly increase its spin rate. Not by much, the increase is tiny, a few parts in a million or less of the total spin. But it is real and measurable, and it is followed by a gradual relaxation back toward the expected spin-down trend. These sudden speed-ups are called glitches. The leading theoretical explanation involves the interaction between the solid outer crust of the neutron star and the superfluid interior. The crust, being solid, is coupled to the magnetic field and the pulsar beam, and it slows down steadily as the pulsar loses rotational energy to radiation. The superfluid in the interior, however, is not so easily braked. Superfluids have no viscosity, and the angular momentum of the neutron superfluid is stored in a large number of tiny quantum vortices. Over time, these vortices become pinned to the crystal lattice of the inner crust, and a rotational lag builds up between the faster spinning interior and the slower spinning crust. When this lag reaches a critical threshold, the vortices suddenly unpin en masse and transfer their stored angular momentum to the crust in a rapid event. A sudden coupling that manifests as the glitch we observe. The crust spins up slightly, the interior relaxes, and the system gradually re-establishes its steady-state coupling until the next glitch. Glitches are genuinely important data. They reveal information about the thickness of the crust, the properties of the superfluid, the coupling mechanisms between different interior layers, and the overall internal structure of an object we can never directly examine. Each glitch is a tiny but precise piece of evidence about what is happening inside one of the most extreme objects in the universe, transmitted to us by the change in arrival time of a radio pulse, crossing perhaps thousands of light years to reach our telescopes. It is one of the more elegant ways the universe has of sharing information about places we will never reach. There are, by some estimates, at least several 100 million neutron stars in the Milky Way alone. Some models place the number at around 100 million. These are not small numbers. Our galaxy contains several 100 billion stars in total, a number so large it defies easy intuition. 100 million neutron stars is a significant fraction of that population. They are not rare in any absolute sense. They are scattered throughout the disk and halo of the galaxy, many of them very old, very cold, and very dim. The challenge is not that neutron stars are rare. The challenge is that most of them are invisible to us. A neutron star that is not oriented so its pulsar beam sweeps across Earth, not accreting from a binary companion, and not young enough to still be emitting detectable thermal X-rays, will radiate very little that any of our telescopes can detect. It will simply be there, an extremely dense, dark, slowly cooling object the size of a city, drifting through the galaxy on whatever trajectory the supernova kick gave it, invisible against the background of space, unknown and undetected. The ones we do detect tend to fall into a handful of categories: young neutron stars, still warm enough to glow in X-rays, pulsars whose beams happen to sweep across Earth, and neutron stars in binary systems where accretion makes them bright X-ray sources. These are a small minority of the total population. Perhaps only a few percent or less of all neutron stars in the galaxy are currently detectable by any method available to us. The vast majority of neutron stars in our galaxy have never been observed, and many never will be with current or foreseeable technology. They are out there, in the dark, between the stars, patient and invisible and extraordinarily dense, carrying information about stellar evolution and the physics of extreme matter that we will, for now, simply have to live without. Among the comparatively small fraction of neutron stars we have managed to detect and study, some have become famous by the standards of astrophysics, objects that have taught us more than others, that sit at the center of iconic images, or that revealed something genuinely new about how the universe works. The neutron star at the center of the Crab Nebula is perhaps the most famous. Born in the supernova of 1054, observed by astronomers in China, Japan, the Arab world, and possibly in the American Southwest, the Crab pulsar now spins 30 times per second and powers the glowing, expanding cloud of gas around it with a steady wind of energetic particles. The Crab Nebula is one of the most studied objects in the sky, and the pulsar at its centre has served as a standard candle, a calibration source, and a laboratory for pulsar physics for decades. Cassiopeia A is another important case, a supernova remnant roughly 330 years old, whose central neutron star is young enough to still be detectable across multiple wavelengths and has been the subject of intensive study, particularly with the Chandra X-ray Observatory. Observations of Cassiopeia A's cooling rate have provided some of the most direct evidence for the presence of a neutron superfluid in the interior. The rate at which it cooled was consistent with theoretical predictions of enhanced cooling from a superfluid undergoing a phase transition. Some neutron stars live in globular clusters, ancient spherical concentrations of hundreds of thousands of stars that formed early in the history of the galaxy. These environments are so densely packed that stellar encounters are common, and exotic binary systems can form through gravitational interactions that would be essentially impossible in the sparse stellar neighborhoods where most stars live. Globular clusters contain a remarkable overabundance of millisecond pulsars, the recycled pulsars we discussed earlier, partly because close stellar encounters provide the conditions needed for mass transfer and spin-up. When two neutron stars find themselves in orbit around each other, a configuration that can arise from the evolution of massive binary star systems where both stars undergo supernova explosions, something remarkable and gradual begins to happen. They spiral together. This process is not dramatic on human timescales. It unfolds over millions or billions of years, driven by an effect predicted by Einstein's general relativity, but not directly observed until the late 20th century. Any two massive objects orbiting each other will, according to general relativity, radiate energy in the form of gravitational waves, ripples in the fabric of space-time that propagate outward from the orbiting system at the speed of light. As the system loses energy to these waves, the orbit shrinks and the two objects draw slowly, inexorably closer together. The first indirect confirmation of this was provided by Russell Hulse and Joseph Taylor, who discovered the first binary pulsar in 1974, a system containing two neutron stars orbiting each other, one of which was a pulsar. Over the following decades, they measured the orbital period of the system with extraordinary precision and found that it was decreasing at exactly the rate predicted by general relativity's gravitational wave emission. The two were awarded the Nobel Prize in Physics in 1993 for this discovery, which was the first observational confirmation that gravitational waves carry away energy. Then came August 17, 2017, the date of the first directly detected neutron star merger. The LIGO and Virgo gravitational wave detectors picked up the characteristic chirp of two neutron stars spiraling together and merging in a galaxy approximately 130 million light-years away. Approximately 7 seconds later, gamma-ray satellites detected a burst of gamma radiation from the same direction. Within hours, telescopes around the world were observing the optical counterpart, a kilonova, a new and rapidly fading point of light. Over the following weeks, the system was observed across the full electromagnetic spectrum, from radio waves through X-rays. GW17U817, as the event was named, became one of the most scientifically productive single observations in the history of astronomy. It confirmed the neutron star merger origin of short gamma-ray bursts. It established neutron star mergers as a major site of heavy element synthesis. It set an extraordinarily tight constraint on the speed of gravitational waves. And it provided the first measurement of the Hubble constant, the rate at which the universe is expanding, using gravitational waves as a standard siren, all from a single event lasting a fraction of a second in a galaxy 130 million light-years away. For many years, astronomers had a reasonable but incomplete accounting of where the elements came from. Hydrogen and helium were products of the Big Bang, forged in the first minutes of the universe's existence before there were any stars at all. The elements from carbon up through iron were produced in the nuclear furnaces of stars, built up through billions of years of stellar evolution and distributed into the galaxy by supernovae. But for the elements heavier than iron, gold, platinum, silver, uranium, iodine, barium, and dozens of others, the picture was less clear. The problem is that forming elements heavier than iron requires the addition of neutrons to existing nuclei. The most efficient way to do this at the very heavy end of the periodic table is through what is called the R process, or rapid neutron capture process, a scenario in which nuclei are bombarded by such an intense flux of neutrons that they absorb multiple neutrons before having time to undergo radioactive decay. This rapid capture builds up nuclei far heavier than any stable isotope, which then decay radioactively to the stable heavy elements we observe. The R process requires two things: an abundant supply of free neutrons and extreme energy. For decades, the leading candidate site was supernovae, which do provide both. But detailed calculations consistently struggle to reproduce the observed abundances of heavy elements, assuming supernovae were the primary site. Something was missing. GW70817 provided the answer, or at least a large part of it. The electromagnetic signals that followed the neutron star merger included a rapidly brightening and then rapidly fading optical source, what astronomers call a kilonova. That was powered by the radioactive decay of freshly synthesized heavy elements. The spectrum of this kilonova matched predictions for R-process nucleosynthesis, confirming that the merging neutron stars had, in the fraction of a second of their final collision, produced enormous quantities of heavy elements and scattered them into space. The numbers involved are staggering. A single neutron star merger can produce roughly an Earth's mass of gold and comparable amounts of other heavy elements. The gold in all the jewelry on Earth, the platinum in catalytic converters, the iodine that your thyroid needs to function. A significant fraction of the heavy elements on and in our planet were very likely forged in neutron star mergers that took place billions of years before our solar system formed, scattered into the interstellar medium, and eventually incorporated into the cloud of gas and dust that became our sun and planets, and eventually us. Some of the heaviest atoms in your body may have passed through a neutron star collision before they found their way to you. One of the deepest reasons neutron stars matter to physics, beyond their intrinsic drama and their role in stellar evolution and their contribution to heavy elements, is that they are natural laboratories for matter under conditions we cannot recreate anywhere on Earth. The densities, pressures, and temperatures deep inside a neutron star are not merely challenging to reproduce in a laboratory, they are, in most cases, physically impossible to achieve by any means available to us, now or in the foreseeable future. This creates an unusual situation. Physics, at its heart, is an empirical science. We develop theoretical models of how matter behaves, and then we test those models against experimental data. But for the physics of dense nuclear matter, matter at and above nuclear saturation density, compressed into the conditions that prevail inside a neutron star, we cannot design an experiment. The conditions exist in nature, in these extraordinary objects, and the universe is generous enough to let us observe them, even if we cannot touch them. So when theorists develop models of nuclear matter at extreme densities, proposed equations of state that describe how pressure and density relate in the neutron star interior, one of the few ways to test those models is by measuring properties of real neutron stars and comparing them to predictions. What is the maximum mass a neutron star can have before collapsing into a black hole? What is the radius of a neutron star of a given mass? How do neutron stars cool? How do they glitch? The most precisely measured neutron star masses are around 2 solar masses. This may not sound dramatic, but it has significant implications. It rules out all proposed equations of state that are too soft, too compressible at high densities, because a sufficiently soft equation of state would predict that neutron stars could not support 2 solar masses against gravity. The existence of 2 solar mass neutron stars tells us something true and specific about the stiffness of nuclear matter at densities several times that of an ordinary nucleus. It is knowledge about fundamental physics obtained by observing objects 1,000 light-years away, and it is knowledge we could not have obtained any other way. General relativity, Einstein's theory of gravity, developed in the second decade of the 20th century and published in final form in 1915, is not background theory when it comes to neutron stars. It is not a correction or a small refinement to an otherwise adequate Newtonian treatment. It is an essential central ingredient in every calculation. The space-time curvature near a neutron star is so extreme that Newtonian gravity fails to describe it accurately in any useful sense. You cannot model a neutron star's structure, its mass-radius relationship, its precession, its orbital decay in a binary, or its gravitational wave emission without the full machinery of general relativity. This makes neutron stars among the best available test beds for general relativity in what physicists call the strong field regime. The regime where gravity is intense enough that relativistic effects are large, rather than small corrections. We can test whether light bends by the amount general relativity predicts. We can measure the precession of pulsar orbits and compare to predictions. We can observe the orbital decay of binary pulsar systems and confirm that gravitational waves carry energy at the rate Einstein's equations predict. In every test so far, general relativity passes. General relativity predicts that time runs at different rates in different gravitational potentials, a phenomenon called gravitational time dilation. Near the surface of a neutron star, where the gravitational potential is extreme, this effect is significant. A clock on the surface of a neutron star would tick measurably slower than one far away in flat space. This is not a hypothetical. It is a consequence of the same physics that makes GPS satellites on Earth need corrections to account for the slightly different gravitational potential in orbit. The difference on Earth is small. The difference near a neutron star is large. Light climbing out of the neutron star's gravitational well loses energy in the process, shifting toward longer wavelengths in a phenomenon called gravitational redshift. Astronomers can, in principle, measure this redshift from spectral features in the X-ray emission from the neutron star's surface and use it to constrain the mass-to-radius ratio. It is one of the more elegant intersections of general relativity and observational astrophysics, using the colour of X-rays from a distant star to probe the curvature of space-time at its surface. There is a popular description of neutron stars as giant atomic nuclei. It is an evocative image and not entirely wrong. The densities involved are similar, and the constituents, neutrons and protons, the particles that make up all atomic nuclei, are the same. It captures something real about how extreme these objects are. But the analogy breaks down in important ways, and the ways it breaks down are themselves illuminating. An atomic nucleus is held together by the strong nuclear force, one of the four fundamental forces of nature, operating at distances comparable to the size of nuclei, binding protons and neutrons together with an attractive force that is strong enough to overcome the electromagnetic repulsion between the positively charged protons. Nuclei are held together from inside by the residual strong force. A neutron star, by contrast, is held together entirely by gravity, the weakest of the four fundamental forces at the particle scale, but the one that dominates at macroscopic distances and large masses. The physics is different, the scale is different, and the result, while superficially similar in density, is a very different kind of object. Nuclei are also uniform in composition, the same density throughout, the same mixture of neutrons and protons, the same forces acting everywhere from center to edge. Neutron stars, as we have discussed, are deeply layered objects: an atmosphere, an outer crust, an inner crust, an outer core, an inner core, each with different composition, different physics, and different states of matter. The analogy of a giant nucleus erases all of this structure and gives a misleadingly simple picture. The more accurate description, though less pithy, is that neutron stars are places where essentially every branch of modern physics meets and is tested simultaneously. Nuclear physics governs the strong force interactions in the crust. Condensed matter physics describes the crystalline lattice and the superfluid. Particle physics may be needed to describe the inner core. Quantum mechanics underlies all of it. And general relativity wraps it all in the geometry of curved space-time. Neutron stars are not one physics problem. They are all of physics at once, compressed into a sphere 12 kilometers across. As extraordinary as individual pulsars are, as clocks, as laboratories, as probes of extreme physics, there is something even more remarkable that becomes possible when you treat many millisecond pulsars together as a coordinated system. Because millisecond pulsars keep time with such extraordinary precision, any small deviation from their expected pulse arrival times carries information about what the radio signal passed through on its way to Earth. And if multiple pulsars in different directions all show correlated deviations, those correlations can be a signature of gravitational waves. This is the concept behind pulsar timing arrays, networks of millisecond pulsars distributed across the sky, monitored simultaneously and continuously by radio telescopes around the world, with the aim of detecting the subtle, correlated distortions in their timing that would be produced by low-frequency gravitational waves passing through the galaxy. The gravitational waves targeted by pulsar timing arrays are very different from those detected by LIGO and Virgo. They have periods of years to decades rather than fractions of a second, and they are produced by the slow grinding in spiral of pairs of supermassive black holes in the centers of distant galaxies. These massive systems orbit each other over timescales of years, radiating gravitational waves so low in frequency that only an instrument the size of a galaxy, a network of pulsars distributed across thousands of light years, could detect them. In recent years, pulsar timing array experiments in North America, Europe, Australia, India and China have each independently reported evidence for a low-frequency gravitational wave background, a faint correlated signal in the timing of many pulsars simultaneously, consistent with the expected imprint of gravitational radiation permeating the galaxy. The galaxy is humming with gravitational waves, and the pulsars, patiently blinking their precise signals across thousands of light years, are the instrument we have used to hear it. It is a remarkable use of a remarkable object, and it represents a genuinely new window on the largest scale processes in the universe. We have spent a good deal of time with the more dramatic properties of neutron stars, the extraordinary density, the intense magnetic fields, the gravitational distortion of light. But there is another extreme worth pausing on, one that is perhaps less visually dramatic but no less astonishing in its implications: the strength of the neutron star crust. The solid outer layer of a neutron star, that crystalline lattice of neutron-rich nuclei in a sea of degenerate electrons, is predicted by theoretical calculations to be among the strongest materials anywhere in the universe. The extreme pressure and density that create this material result in a crust far stiffer and more resistant to deformation than any material we could make or find on Earth. Diamond, the hardest naturally occurring substance on our planet, famous for its resistance to scratching and its extraordinary rigidity, would be almost immeasurably softer than neutron star crust. The ratio of breaking strengths is roughly 10 billion to 1 in the neutron star's favour. This matters for several reasons. The crust must survive not only the crushing pressure from the interior pressing outward, but also the stresses imposed by the star's rotation, the centrifugal effect of spinning potentially hundreds of times per second, and the stresses imposed by its magnetic field. In ordinary pulsars with modest magnetic fields, the crust handles these stresses without difficulty. In magnetars, where the magnetic field is 1,000 times more intense, the stresses eventually exceed even what neutron star crust can bear, and starquakes result. The fact that even the strongest material in the universe eventually yields under magnetar conditions gives some sense of the scale of the forces involved. It is not that neutron star crust is fragile, it is that magnetar fields are so unimaginably powerful that they can fracture something 10 billion times stronger than diamond. The universe, when it decides to be extreme, does not do things by halves. The term multi-messenger astronomy describes an approach to studying the universe that uses not just light, not just electromagnetic radiation across the spectrum, but all the channels through which the cosmos transmits information: gravitational waves, neutrinos, cosmic rays, and electromagnetic radiation together. It is a new way of doing astronomy, made possible by instruments and collaborations that simply did not exist until recently, and neutron stars are central to it. They produce gravitational waves through their mergers. The spiral in and collision of two neutron stars sends a distinctive chirp of space-time ripples across the universe, detectable by instruments like LIGO and Virgo. They produce neutrinos through their formation in supernovae, The vast neutrino burst of a core collapse supernova, like the one observed from the nearby supernova SN 1987A, was the first detection of neutrinos from a known astrophysical source other than the Sun, and it arrived at Earth several hours before the supernova was visible in light, confirming theoretical predictions about the sequence of events in stellar core collapse. They produce electromagnetic radiation in essentially every band, radio pulses from pulsars, thermal X-rays from their cooling surfaces, energetic X-ray bursts from accreting systems, gamma rays from magnetar flares and merger jets. The power of multi-messenger astronomy lies in the combination. Gravitational waves alone tell you about the masses and spins of the merging objects and the dynamics of the collision, but relatively little about the environment. Electromagnetic signals alone give rich spectral and timing information, but cannot easily penetrate the dense environments of some events. Neutrinos carry information about processes buried deep inside the star, inaccessible to any light. When you combine all three, as was possible for GW 700-817, where gravitational waves, gamma rays, optical emission, X-rays and radio waves were all detected from the same event, the result is a far more complete picture than any single messenger could provide. Neutron stars are not merely subjects of study in the era of multi-messenger astronomy. They are, in some ways, the most useful objects it has yet studied, the most communicative, the most informative, the most willing to reveal their nature across every channel the universe provides. And so we arrive at the end of our journey through one-on-one facts about neutron stars. If you have made it this far with your eyes open, we hope the journey has been a gentle and pleasant one. And if somewhere along the way, perhaps somewhere between the magnetar flares and the millisecond pulsars, or in the layered interior with its neutron drit and its superfluid core, or in the quiet discussion of 100 million dark and invisible objects drifting through our galaxy, you found yourself drifting as well, then the neutron stars have served their purpose. They are, in the end, remarkable objects to spend time with, not because they are violent, though they can be, and not because they are dramatic, though they often are, but because they sit at the intersection of so many things we find beautiful and profound: the death of stars and the birth of new matter, the extreme physics of density and gravity and magnetism, the patient accumulation of knowledge by generations of astronomers looking at the sky with instruments of steadily increasing sensitivity, and the way that understanding one extraordinary thing will eventually teaches you something true about the nature of everything. Neutron stars are city-sized and sun-massed and trillion-ton teaspoon dense. They spin hundreds of times per second and cool over billions of years. They forge gold in their collisions and probe general relativity with their orbits and reveal the interior of dense matter with their glitches. They exist in their millions throughout our galaxy, most of them silent and dark and patiently waiting in the spaces between the stars, cooling by imperceptible degrees in the long quiet of cosmic time. There is something restful, if you let it be, in the image of all those dark neutron stars out there. Extraordinarily dense, extraordinarily small, and enormously patient. They have been cooling since before our solar system existed. They will continue cooling long after it is gone. They are in no hurry. They have nowhere they need to be, neither do you tonight. Let your breathing slow. Let the facts settle gently wherever they have landed. The neutron stars are out there, and they will still be extraordinary in the morning. Good night.